Thank you for joining me. I'm glad to have you here. Last time we discussed about the reflection of light on plane surfaces. It's actually plane mirrors. Today I want us to look at the reflection of light at spherical surface. And when we talk about spherical surfaces or spherical mirrors, we talk about the concave mirror and the convex mirror. Let us look at some of these. We have a concave mirror, and we have the second one, convex mirror. Okay, we're not going to look at the formation of image by these mirrors. We just want to look at some vital points about concave mirrors and convex mirrors. To start with, if this is a sphere, and of course we have this, if the silver surface, if the outside of this sphere is silver, we have what we call concave. Then if the inside surface is silver, for example, we have this. If the inside surface is silver, now we have this point is the pole, this point is the principal focus, and this point here is our center of curvature. The same thing with this. So this is a convex mirror. Otherwise, this it can be called convex, or you call it a diverging mirror because it diverges incident rays. Whereas this one is a concave or converging mirror. Now, this is the pole. Of course, the pole is the point that subdivides the mirror into two equal parts. We have somewhere here the principal focus, and here is the center of curvature. The distance between here, the principal, the pole, and the center of curvature is the radius of curvature. While the distance from the principal focus to the pole is the focal length. Now, the nature of image produced by these two mirrors. For this one, the image produced is always, so the image is always one. The image is always diminished. The image is always diminished. Two, the image is always erect. Either you say it is erect or upright. The image is always upright. Thirdly, the image is always virtual. It's always virtual. It is virtual because it is formed at the back of the mirror. But for this one, which is the concave, the image produced, the image is dependent. The image is dependent on the position of the object. It is always dependent on the position of the object. Where the object is placed will determine the nature of image you will get. For example, if the object is placed beyond C, the image you will get is a diminished, inverted, and real image. It is real because, of course, this is the back of the mirror, this is the front, this is the reflective surface, which is the front of the mirror. The image is formed in front here. So if the object is placed beyond C, we will get a diminished, real, and inverted image. Now, if we shift it to C, the image will be a little bit big. Of course, it will be as big as the object. So when the object is placed at C, the image is same size as the object. The image is still inverted and it is real. Now, if we move it between C and F and place it between C and F, that the object, if the object is placed here, the nature of image we will get is, you will get a magnified image, still inverted and real. Now, if we place the object at F, of course, the image will be formed at infinity. No image is seen, but in practical terms, we can say that yes, it is formed at infinity. Now, if we move your object to between F and P, at this point, you will now get a magnified and upright image. So that is why we have concluded that the nature of image produced by this mirror is highly dependent on the position of the object. So these are the various positions, just like we have said. Now, the uses, they are used differently. They have their different uses. For example, the concave mirrors are used as driving mirrors. For these concave mirrors, they are used as shaving mirrors, please. I'm not driving. They are used as shaving mirrors. They are used as dentist mirrors. Next one, they are still used as satellites. They can also be used in the headlamp of motor vehicles, or even in torches. They are used in torches as well. Then they are used as reflectors in reflecting telescopes and microscopes. Then there are other uses apart from the dentist's use, apart from the use as shaving mirrors and all that I've mentioned. Now, for this one, like we said, that always produces a very diminished image. It has a very wide field of view or wide range of view, whereas this one has limited range of view. This one has a wide range of view. Now, it can be used as a driving mirror in our various vehicles, in scooters, motorbikes. They are used as driving mirror. They can also be placed as strategic locations in supermarkets just to monitor what the activities that are going on in various supermarkets. So they have discussed their uses, the uses of each of them. Now we'll talk of the calculation. Now for the calculation purpose, we have a mirror formula. Generally, mirror formula is expressed as 1 over f is equal to 1 over u plus 1 over v. So this is a general formula for mirror. It is applicable to both convex mirror and concave mirror. But there are important points I want us to note about these two mirrors. One of these points is that, yes, just like we have said that the focal length is between this and this. So we said that for the focal length is half of the radius of curvature. This is the radius of curvature. Half of it is the focal length. Therefore, we now have that f is r over 2. Or, if we want to get our radius of curvature, if we find our principal focus, we multiply it by 2, and it will give us our radius of curvature. Secondly, for convex mirrors, they have negative focal length because it is forming a virtual image. They have negative focal length. Therefore, f, from this formula, f is negative. And because the image produced is always negative, we have v also. We have both f and v negative. Third point, concave mirrors have positive focal length. That means for concave mirror, f is positive. But if the object distance is less than the focal length, then v will give us a negative. Or if the object distance is less than focal length, if the object is placed between f and p, and of course, if it is placed between f and p, the image that will be produced is a virtual and upright image. So at that point, that is the only condition that Now, the fourth point I want us to note is that distances of both real objects and the real images are all positive. From the question, once the question says that both the object distance and the image distance formed is real, then both u and v will be positive. Now, distances of virtual objects and images are negative. Now, if the object is real, if the object is virtual, maybe image produced is virtual also, then both, at that point, we have v to be negative, and then u also at that point is negative. Okay, let us take one or two calculations. For the first one, the image of an object is located 6 cm behind a convex mirror. If its magnification is 0.6, calculate the focal length of the mirror. So we have here that if, let's say here, the image of an object is located 6 cm behind. So since the image of the object is located 6 cm behind, V will give us minus 6 centimeter. If its magnification, here they say magnification is 0.6 and nothing else. So we are asked to calculate the focal length of the mirror. F is unknown. Now, how do we tackle this problem? So I want you to note that magnification is image distance all over the object distance. Now, once we have that assurance, we will now have that if we substitute, we have 0.6 is equal to V. V is minus 6 all over U. From here, we can cross multiply. If we cross multiply, we have minus 6 is equal to 0.6 U. Make the subject, U will give us minus 6 all over 0.6. And minus 6 over 0.6 will give us minus 10 centimeter as our object distance. So having gotten our U, we have V here, we can proceed to get our F. Now for us to get our F, we have that F is equal to 1 over F is equal to 1 over U plus 1 over V. The general formula first. After writing the general formula, you begin to, at this point now, you can introduce the negative or the positive. Another point you need to note is that for a convex mirror that has both negative V and negative U, if you are asked to assume F is negative, this one is negative, you cannot use both negative signs at the same time. So if you want to get U, sorry, if you want to get V, you use positive. At the end of the day, your answer will be negative. But if you want to get your F for a convex mirror, you want to get your F, and the F is negative, you use positive here. So that at the end of the day, your answer will be negative value. So back to what we are discussing. So since we have our formula first, we can now substitute. 1 over F is equal to 1 over U. Our U is minus 10. Now, instead of plus, or you can say 1 over minus 6. And of course, 1 over minus 6 is something as writing minus here. So we proceed with this. 1 over F is equal to LCM of 10 and 6 will give us 60. 10 divides 60 will give us 6. 6 times minus 1 will give us minus 6. You retain your minus here. 6 divided 60 will give us 10. Then, which will give us 1 over f equals minus 6 minus 10 will give us minus 16 all over 60. Now we can even cross multiply to make f the subject. F will now give us 60 all over 16. And then 60 over 16 will give us minus 3.75 centimeters. Therefore, we can have that our f is minus 3.75 centimeters. Okay. Now let us take the second question. Having solved this one, we can go ahead to take the second question. The second question says, a concave mirror of radius of curvature 40 centimeter. A concave mirror of radius of curvature 40 centimeter forms a real image twice as large as the object. Forms a real image twice as large as the object. The object distance is dash. Now we have solution. From the question, they said a concave mirror of radius of curvature 40 centimeter. The radius of curvature here is 40 cm. Forms a real image, and of course when you hear real image, V should give you positive. The real image V is positive. Though they said here the images are twice as large as. Twice as large as, that is magnification. That means magnification is 2. The object distance is what we are looking for. Now at this point we don't have V. How do we get V? Now we also say, recall that magnification is V all over U. Now in this case, magnification is 2. 2 is equal to V. We don't have V all over U. We still don't have U. So what do we do? Make V the subject. If we make V the subject, V will now give us 2U as our V. At this point, we substitute into the mirror formula. 1 over F is equal to 1 over U plus 1 over V. Remember that this is a real image. V is expected to be positive. And in this case, since radius of curvature is 40, recall that we say that focal length is radius of curvature over 2. Therefore, we now have here that our F is 40 over 2, giving us 20 centimeters. So we can bring it here. 1 over 20 is equal to 1 over U plus 1 over our V is 2U. Having gotten this, this side is still like terms. We say 1 over 20 is equal to LCM of U and 20 is 20. Sorry, U and 2 is 2U. U into 2U will give us 2. 2 times 1, 2 plus 2U into 2U give us 1. 1 times 1, 1, which will give us 2 plus 1, 3 all over 2U, which will now give us 1 over 20 is equal to 3 over 2U. Now, cross multiply, we have 2U is equal to 3 times 20 is 60. Therefore, U is equal to 60 over 2, which will give us that U is equal to 30 centimeters. So this is our object distance. Remember, this formula is also F is equal to UV all over U plus V. So if you substitute these values into V, you will still get 30 centimeters. Okay. Now, we'll take the next question. Of course, this question came out 2024 NECO, and it's still part of it. Remember, light question is every year question. Now, we'll take this question. A man placed a shaving mirror at a distance of 20 centimeters from his face. I repeat, a man placed a shaving mirror at a distance of 20 centimeters from his face. If the image of his face appears to be at a distance of 30 cm behind the mirror, calculate the radius of curvature of the mirror. Okay. From here, we can have, let's say, a man placed a shaving mirror. Of course, we don't know what we call shaving mirror. A shaving mirror is a concave mirror, so we should expect F to be positive. So, a man placed a shaving mirror at a distance of U is 20 cm from his face. If the image of the man appears to be at a distance of 30 cm, that means if the image of the man appears to be at a distance of 30 cm behind the mirror, since it is behind, we have minus 30 centimeters. Calculate the radius of curvature. R is what you're looking for. Remember that F is not here. Also, R is 2F. So we proceed to get our F. Once we get our F, we multiply it by 2, and it will give us our radius of curvature. So we have 1 over F is equal to 1 over U plus 1 over V, which will give us 1 over F equals 1 over U. U is 20. Now at this point, minus 1 over 30, because the V is negative 1 over 30, which will give us 1 over F equals, outside of 20 and the 30 will give us 60. 20 divided 60 will give us 3. 3 times 1, 3 minus 3 divided 60, 2. 2 times 1, 2, which will give us 1 over F equals 3 minus 2, 1 over 60. So, because this is inverse, 1 over F means inverse. Turn this upside down, or you do the multiplication. F times 1 is equal to 1 times 6. At the end of the day, you now get that F is 60 centimeters. In other words, since we're looking for R is 2F. R will therefore, radius of curvature of the mirror is 2 times 60. And 2 times 60 will give us 120 centimeters. So this is the radius of curvature of the mirror. Okay, at this point, this is where we'll end the lesson. We still have, there are other examples. If you take past questions, JAMB, WAEC, and NECO, you will see so many questions. Every year, you must see questions from mirrors, either from plain mirror or from curved mirror. This is where we'll end the lesson. Thank you so much for your patience, for being here with me. Thank you. I appreciate you. We'll meet some other time. Please do not forget to hit the like button, share this video with others so that they can have this knowledge. Thank you very much.